Hello, and welcome to statistics. Now, I know this is most people's least favorite subject. We're going to try to walk you through not statistics in general, but focus on what you need to handle for your Step 2 CK exam. I understand that many people have, over the years, been frustrated by statistics, and I have a sense of that frustration. It's kind of like getting locked out of your house at the end of the day. You come home, you're standing there, and all you need is a simple key to walk through the door, go into your house, and life goes on. But you discover you're missing that key, you're locked out, and that's frustrating. All you need is a simple key. You walk in, you go about your business. Well, dealing with statistics questions on your Step 2 exam is really about the same thing. What you need is a set of simple keys. You don't need to understand statistics in general. What you need to understand is some simple issues in statistics, and with that in place, you can then unlock the questions and move on with the process. What are the basic things you need to know about biostatistics for your Step 2 CK exam? Well, you need to know some basic probability rules. We'll cover that first. Then you need to be able to understand the normal distribution, and in particular, the standard percentages relative to standard deviation units in the normal distribution. You need to understand confidence intervals, the concept, the calculation, and then the interpretation of confidence intervals. You need to understand p-values, hypothesis testing, how we use this p-value in making statistical decisions. And finally, frankly, the least important of this content, you need to understand selecting the appropriate statistical test, how to decide whether it's a chi-square, a t-test, or a correlation coefficient, for example. That's our basic agenda. Let's get started. And we begin with probability and probability rules. You don't have to understand, once again, all the details about probability. What I do need you to understand is simple mechanics for how we're going to combine probability. There's two basic issues here. First is how we're going to combine independent events. Independent events we're going to combine by multiplying. So if you get nothing else out of what I'm saying here, get down the simple mechanics. For independent events, you multiply. Now, what do I mean by independent events? Well, I mean, if you know what happened before, it tells you nothing about the next set of probabilities. Independent events are simply fixed probabilities, and knowing previous events doesn't change your understanding of future events. The most common way we always think about this is to think about flipping a coin. You take a coin, you flip it once, twice, 3 times, 4 times, and it comes up heads all 4 of those times. You've now just gotten 4 heads in a row. What's the chance of getting a head on the last and the 5th final flip here? Well, it's still going to be 50%. Knowing I got a bunch of heads in a row does nothing to change the probability. The coin remains a 50-50 chance each and every time I flip it, regardless of what you've seen prior to that. Now, because the probabilities remain constant, your life is easy, because all you have to do is take these constant probabilities and combine them by, well, multiplication. So, you know the chance of getting a head on a single coin flip is 50%. But what's the chance of getting 2 heads in a row? If I flip the coin twice, what's your chance of getting a head and then another head? The answer here is, again, multiplication. It's 50% times 50%, or 25%. Relatively straightforward. Well, what then is the chance of getting 3 heads in a row? Well, once again, you simply multiply. This time, you multiply 3 times. 0.5 times 0.5 times 0.5 again, or scientific notation is actually very useful here, 0.5 to the third. Or multiplied all the way out, 12.5%. What I hope you see here is this is a simple rule, and therefore you get a simple answer to the question. This is nothing difficult. You simply multiply and you get your answer. How many times do you multiply? Depends what the question asks you for. If it says 2 times, and you multiply 2 times. If it says 3 times, you multiply 3 times. The second way we talk about combining probabilities is combining mutually exclusive events. Now, independent events we were talking about across multiple coin flips, across multiple trials, across, said differently, multiple different events. Mutually exclusive, we're talking about within a single trial, a single coin flip, within a single event. Now, you know this next one intuitively. What we're going to do with mutually exclusive events is simply add. We take the 2 or the 3 or the 4 probabilities that we're working with, and we add them together to sum to the answer we want to end up with. Simply, if I flip a coin on a single coin flip, what's the chance of getting either a head or a tail? Well, you know that. It's got to be 100%, because I take the 50% for head, the 50% for tail, and I simply add them together. Heads plus tails, in other words, is 100%. All you need to remember about mutually exclusive events is you take them, you add, and you have the answer. Let's look at this a little bit differently. Here we have 2 sets of circles. These circles represent pieces of Venn diagrams, which are ways to, well, visually look at some logical issues. What we have on top are 2 circles, circle A and circle B, without any overlap whatsoever. Well, this is what we mean by mutually exclusive. Quite simply, if you're in A, you can't be in B. If you're in B, you can't be in A. One, in some real sense, excludes the other. One occurs, the other one can't occur. If I want to know what is the joint probability, that is, in some sense, the total probability of both of these circles, the joint area of both of these circles, another way to think about it, it's obvious how I'm going to answer that question. I'm simply going to add together A plus B. I take the 2 areas, add them together, there's no overlap, and the answer is fairly straightforward. But now let's take a look at the second set of circles. The second set of circles, once again, the same size, once again, circle A and circle B, but now we have something different here. Here we have overlap. It's possible to be both A and B at the same time. We call this non-mutually exclusive. And all that means is you could be both at the same time. We have this middle area, which I'll shade in yellow so you see what I'm talking about, which is part of A but also part of B. Okay, now simple question. If I simply at this point add A and B together, do I get a number that's too large, too small, or just right? Well, if you just think about that for a moment, I should get a number that's too large, because I counted that yellow area once as part of A, and then I end up counting it a second time as a part of B if I simply add A and B together. Clearly, just adding A and B together will not give me the right answer. It gives me a number that's way too large. What I need to do is, well, when I add A and B together here, I count that yellow area twice. And if I just want that yellow area once, what I need to do is subtract out one occurrence of that yellow area. What I need to do, therefore, is have a sense of what the value is of that particular overlap, that yellow area. Now, what I'd love to have is empirical data. I'd love to have actual empirical data that tells me in the real world what is the actual overlap between these two. But not having that, we have a simple device. I'm going to assume independence between A and B, and by assuming independence, I can estimate that overlap area by simple multiplication. I'm going to estimate the joint area A and B share by simply taking A times B. That A times B becomes, in a very real sense, a correction factor. So, if I want to know what is the joint area of A, B, or both, well, I simply am going to begin by adding A plus B, and then use my correction factor minus AB. Once again, if I want to know the chance of A, B, or both, it's simply A plus B minus AB. Why minus AB? Well, because when I simply take A and B and add them together, I've double counted that yellow area. If I want to know A, B, or both, I don't want that yellow area counted twice, as I do when I just add. I want that yellow area counted once. Hence, I simply correct by subtracting out one occurrence of that yellow area. It's therefore A plus B minus the correction factor AB. Let's talk about what this might look like as we work through some simple numbers together. You have some simple probability numbers given to you right above these circles in your syllabus, and let's work through the problem they imply. The question, or the information rather, tells you the chance of meeting someone who's obese is 30%. The chance of meeting someone who's diabetic is 10%. Given those figures, here's a simple question. What's the chance of meeting someone who's obese, has diabetes, or both? Obese, diabetes, or both? Well, the way to start is obvious. We take obesity, 30%, diabetes, 10%, and we simply add them together. But wait, that doesn't solve the problem, because we know, you don't need to be told, you know this already, obesity and diabetes are non-mutually exclusive. You know that because you know it's possible for a single person to be both obese and diabetic. Frankly, it's a high probability if you're one, you're more likely to be the other. So I can't simply add those two together and stop. I need to subtract out, again, that shared area, because when I take obesity and diabetes, I have that area counted twice, just like in the previous diagram. Well, once again, what I'd love to have is empirical data telling me the overlap between obesity and diabetes. But not having that, I'm going to fall back on the simple convention. I'm going to assume independence, and I'm going to multiply. I'm going to multiply the probability of obesity times the probability of diabetes to get my correction factor. Hence, I have the answer to my question, which is obesity plus diabetes. 10% plus 30% gives me 40%. When I multiply those two together, that gives me 3%, and that's my correction factor. The answer, therefore, what's the chance of meeting someone who's obese, had diabetes, or both, is not 40%, but 40% minus the 3%, therefore 37%. Understand again how we got the 37%. We began by first adding the two together, then we multiplied them to get the correction factor, then we subtracted out the correction factor, and we end up with the answer here, 37%, obesity, diabetes, or both. Now, just pause and look back at that, because each of those steps were, come on, admit it, fairly simple, yes? What makes the question hard is you have to remember to do each of the steps in order to arrive at the full answer at the end. And that is, by the way, a pretty good template for a USMLE Step 2 CK question. The question's in general not about doing some big mental leap, but about a series of small steps to literally walk yourself from where you start to what the answer is. With those basic rules in mind, independent events you multiply, mutually exclusive events you add, non-mutually exclusive events you're going to add and then subtract out the overlap area, which is simply the product of the two probabilities added together. Let's go ahead and do some simple practice questions together. Here's the first question for you. If the chance of having diabetes is 10%, what's the chance that 3 people, selected at random from the population, will all have diabetes? Well, the issue here is 3 separate people. Therefore, the issue here is about independence. Therefore, I'm going to multiply. Multiply what? 10% times 10% times 10%, or 0.1 to the third, or 0.001. All those are acceptable answers. Notice once again that scientific notation is actually, well, simplifies your thinking here. You just take the core probability, 10%, put it to the third power, and you have the answer. The third power because there's 3 people. Second question. 183 people have a particular surgical experience. A year after that surgery, 90% of them are still alive. 2 years afterwards, 75% are still alive. 3 years afterwards, 50% are still alive. And finally, 4 years afterwards, 40% are still alive. That's the starting data, and here's just a few simple questions about that data. First, an easy question, I hope. What is life expectancy following this surgery? Well, you remember from our previous lectures in epidemiology, life expectancy is a synonym for median survival time. 50% are the percent alive at the end of the 3rd year, and so life expectancy after this surgery is 3 years. We simply go to 50%, that's the median, and therefore that's life expectancy. Let's ask you a different question. Given that you have the surgery, the chance of being alive after 3 years is 50%. But suppose the patient's still alive after 2 years. Given that they're alive after 2 years, what's the chance of being alive after 3? Given that you're still alive after 2, what's your chance of being alive after 3? Well, the way I want you to think this through is to first reframe the question so we get rid of percentage. Because, come on, admit it, percentage confuses many of us. Percentage distorts our thinking, so let's get down to the root of what we're really talking about. Forget that there's 183 people had the surgery. Think that 100 people had the surgery. And of that 100, 90 were still alive after year 1, 75 still alive after year 2, 50 alive after year 3, and 40 alive after year 4. And we can do this because, well, that's what percent means, out of 100. That means that that 90 is a subset of the 100, okay? It means that 75 is a subset of the 100, okay? It means that 50 is a subset of the 100. But it also means that 75 must be a subset of the 90, because you must be alive after 1 year if you're going to be alive after 2. That also means that 50 is not only a subset of the 100 and a subset of the 90, but it must be a subset of the 75. So the 3-year survival rate is 50%. But suppose you're alive after 2 years, what's your chance of being alive after 3? Oh, well, that's easy. We had 75 people alive after 2 years, of which 50 made it to the 3rd year. The way we represent that mathematically is a simple ratio, 50 out of 75. Mechanically, you take the number where you're ending and put it on top, and the number where you're focused to begin, alive after 2 years, on the bottom. Therefore, 50 divided by 75, and therefore the answer, 67%. That's it. Very straightforward. And if you didn't know how to do this before, that's okay. You know how to do it now. Make sure you're with me by just reframing a different question here. Suppose you're alive at the end of 1 year. What's your chance of being alive at the end of 4? Suppose you're alive at the end of 1 year. What's your chance of being alive at the end of 4? That's easy. It's going to be 40 out of 90. 40 out of 90. Once again, I put the number where I'm stopping, ending on the top, and the number where I'm told to start after 1 year on the bottom. 40 out of 90 answers the question. The whole point of these probability exercises is not that I necessarily expect all of you to be familiar with them, but I expect you to learn the basic mechanical rules by which you will derive the answer and therefore get the question right on your exam. We now leave behind probability.